Okay, so the first thing we are going to look at today is why the lattice formation enthalpy is exothermic. And before you can explain this, you need to be able to explain what you mean by lattice enthalpy. Okay, so we have to be happy that there are two types of lattice enthalpy. So we've got lattice formation enthalpy and then lattice dissociation enthalpy. Okay, so the lattice formation enthalpy, we'll call it LFE. That is equal to the energy that is required for a lattice to be formed from its constituent ions in the gaseous state. So if we take sodium chloride as an example, the lattice formation enthalpy for sodium chloride would be a sodium ion in the gaseous state and a chloride in the gaseous state to get down to your sodium chloride solid. Okay, and then your lattice dissociation enthalpy is going to be exactly the opposite. So it's going to be the enthalpy required to actually break apart 1 mole of sodium chloride as a solid to go to your sodium plus ions as a gas and your chloride ions as a gas. Okay, so we go in the forward direction, we've got a lattice formation enthalpy. And if we go in the reverse direction, we've got a lattice dissociation enthalpy. Okay, so we can look at these two different types of enthalpies, and we can look at the lattice dissociation enthalpy to explain why the lattice formation enthalpy is exothermic and therefore negative. So what I want you to do is pause the video and then see if we can look at predicting what's going to happen with the lattice formation enthalpy and the lattice dissociation enthalpy. Okay, so we've got our lattice dissociation enthalpy, and we can draw that, what's actually going to happen, in terms of diagrams. Okay, so we can look at our positive sodium ion surrounded by a negative, slightly bigger chloride ion. And we've got a sea of those in the lattice structure. So we've got chloride ions and sodium ions surrounding each other in a 3-dimensional structure. Okay, and then obviously the lattice enthalpy is the energy required to break down 1 mole of those to form sodium ions and chloride ions that are now no longer bonded in a lattice structure. So we can obviously see that here there's going to be a lot of attraction. Okay, so to break those apart, it's going to take us inputting some energy. Okay, so therefore, that reaction is going to be endothermic. If we go back, we can now look at predicting and using this to explain what's going to happen to the lattice formation enthalpy. So what I want you to do, pause the video and see if you can use this to explain why the lattice formation enthalpy is negative and therefore exothermic. Okay, so we've set up our reaction of a sodium ion and a chloride ion reacting together to form my 1 mole of sodium chloride. Okay, so in the forward direction, that reaction is my definition of the lattice formation enthalpy. Okay, and in the backward reaction, that reaction is my definition of the lattice dissociation enthalpy. We've already seen in this reaction there's an attractive force in our sodium chloride So it takes energy to remove those two ions apart from each other. Okay, so to separate them. So therefore, this is going to have a positive delta H. Because my lattice formation enthalpy is exactly opposite and going in the opposite direction, it therefore must have a negative delta H. And that's why my lattice formation enthalpy is negative, and when you draw it in a Born-Haber cycle, it's going to be a downward arrow.